So here's sample problem 5. We're going to provide a rough sketch of his NMR. Remember, the first thing we should do is fill in the hydrogens right here. And then remember, we saw before that benzene rings are symmetrical objects. So this molecule does possess a line of symmetry, and that line of symmetry is right here. So now we're ready to label our hydrogens. We're going to call the methyl hydrogens the A-type hydrogens. Those are clearly different from these hydrogens right here. These would be the B-type hydrogens. Notice they're across that symmetrical line there. These hydrogens are definitely not the same. We're going to call those the C-type hydrogens. And that last hydrogen, it's the only one on the benzene ring that actually lies on the plane of symmetry, so that makes him different than B and C. So we're going to call him the D-type hydrogen. All right. Now, what are the shiftings here? Well, remember, since the hydrogens are connected to the benzene ring and the benzene ring has multiple or double bonds, then the hydrogens connected to benzene should be more shifted. So here's our rough sketch right here. We would see, of course, 4 peaks, one for each hydrogen here in the sample. And obviously the least shifted one would be the methyls hydrogens. They are the furthest from the benzene ring. So that would be this peak right here. And the hydrogens on the benzene ring are these 3 peaks right here, D, C, and B. Now, they're roughly in the same area, so we're grouping them up right here. What you see in front of you here is just really the theoretical number of peaks and where they would be on the NMR. But let's talk about the reality here for a second. If you really ran this molecule through the NMR, this is actually what you would see. And basically what you're looking at is that those B, C, D hydrogens, they're all kind of lumped together like that. And let's take note of where these would actually appear. There's a constant here. Typically, hydrogens on a benzene ring peak around 8 to 6.5 delta units or ppms. So seeing a bunch of squished together peaks like that between 6.5 and 8 is evidence of a benzene ring. If you were on a multiple choice exam, you would definitely at this point rule out any answers that don't have a benzene ring in them, or you'd suspect those first as possibly being the answer. Now let's look at those A hydrogens. They are not directly connected to the benzene ring, but they are technically not too far from it, so they would peak at around 2.3 ppms or delta units. Now let's go back to those benzene ring hydrogens. Why do they peak around 6.5 to 8? And think about that. That's very shifted. Remember, usually the chart goes from 0 to 10, so they're really technically very far downfield. Let's understand why they're so shifted. But before we do that, we have to go back to a basic concept that you might have learned in physics. And that's basically this. If you have an electron here like this, and an electron accelerates through space, this is just a fact that we have to accept, that when charges move through space, they create magnetic fields around them. So since electrons are charged, they too, as they move, create magnetic fields around them like this. So let's go back to our benzene ring here. And let's kind of get a better perspective here. Let's kind of put him on his side. Let's tilt him a little bit right here. And let's see what happens here. First, let's take those pi bonds that we see in the benzene ring and let's turn them into actual electrons like this. And then let's place our molecule in the NMR and turn on the applied B magnetic field. Now, if you remember before from an earlier chapter, benzene rings have resonance. Those pi bonds can circulate around the ring, or we can say the electrons that make up the pi bonds can circulate around the ring. And when those electrons circulate around the ring like this, remember, we just learned that when electrons move, they create magnetic fields around them. So notice that dark blue arrow there. Let's pretend that's the magnetic field that those electrons are creating. And let's focus on these hydrogens here on the left in the yellow box. Notice how the magnetic field created by the electrons are moving right through those hydrogens. In fact, let's get a close-up view of what's going on right there. And also, let's go back to our formula that gives us an idea of how much something should be shifted. Here is our B effective equals B applied minus B local. Now remember, this right here, this B field, is created by the electrons, remember, that are moving through the benzene ring and circulating like this. And remember, we also have the B field that the NMR machine is creating. So notice in this yellow box right here, you got two B fields going on. And notice their direction. The B field by the electrons in the benzene ring is going downward this way. And the B field created by the NMR is also headed in a downward direction like this. So think of it this way. The B field created by the moving electrons, since it's going in the same direction as the B field by the NMR machine, think of it almost as it's helping out that B field. It's adding to it. That means that in our formula, the B applied right here is going to be even bigger. And think about what that does to our equation. Making that value larger means the B effective for those hydrogens in that yellow box is also going to be bigger. And we saw before, remember, if you have a high B effective, any proton or hydrogen in the NMR that has a high B effective is going to have a high energy, meaning a lot of energy necessary to bring it into resonance. And if it requires a lot of energy to bring you into resonance, you are going to peak more downfield. Some vocab here. The name of this phenomenon is called diamagnetic anisotropy. So let's go back to our rough sketch here. This is why the BCD hydrogens right here are very downfield and shifted. That's why they're appearing at around 6.5 to 8. So notice diamagnetic anisotropy has a very powerful shifting effect. But it's not just limited to benzene rings. Even just simply doubly bonded molecules can participate in it. For example, let's take this alkene right here and let's turn the pi and the sigma bond into electrons. And again, let's throw him into the HNMR and turn on our applied magnetic field. These electrons in this molecule also move around and circulate. And remember, if they move around and circulate, it means they create magnetic fields. So notice, look at the hydrogens here directly connected to those carbons. The B field created by that electron movement is influencing those hydrogens. And also, of course, they're being influenced by the B field created by the NMR. And if you get a close-up view here of what's going on, again, you see that additive effect. The B field created by the electrons is going in the same direction as the B field of the NMR, therefore increasing the B applied field, and therefore increasing the B effective on that hydrogen. So it's no surprise that if you put this molecule in the HNMR, you would expect to see these hydrogens right here peak at around 4.7, almost halfway down the chart. Notice they're not as shifted as the hydrogens on the benzene ring, but they do have a sizable shift to them. However, it's not always that the B created by the electrons is in the same direction as the B created by the NMR. Look at this example right here. These are two carbons that are triply bonded that have hydrogens attached to them. If we threw this molecule in the HNMR and turn on the applied magnetic field, the electrons in the triple bond, they would move as well, but they would create a magnetic field that runs this way, like this. Notice, focus on this top hydrogen here in the yellow box. When we get a close-up view of it, notice the B field created by the electrons is moving in the opposite direction of the applied magnetic field. So for this case, we don't expect the B effective to be as high as in the other two examples. In fact, if you put this molecule in the HNMR and looked at the data, this hydrogen right here would peak at around 2.4 ppms. Notice that's not very shifted. So hydrogens bonded to triple bonded carbons are not going to be as shifted as alkene hydrogens or hydrogens on benzene rings. But the reason behind how each one shifts is again diamagnetic anisotropy.